As we embark on this simulated journey into the heart of the Milky Way, it's important to understand the scale and nature of the region we're exploring. The center of our galaxy, also known as the galactic center, lies approximately 26,000 light-years from Earth in the direction of the constellation Sagittarius. Although this distance might seem unimaginably vast by astronomical standards, it's actually quite close. Thanks to advances in telescopes and spaceborne observatories, scientists have been able to peer into this dense region and collect data that helps us build a detailed picture of its structure and composition. One of the most striking features we immediately encounter in this central region is an enormous concentration of stars, packed much more densely than in the quieter suburbs of the galaxy like our solar neighborhood. Imagine a crowd so tightly packed that stars are separated by only a fraction of the distance typical between stars in less dense areas. In the vicinity of the galactic center, stars can be just a few thousand times the distance between Earth and the Sun from one another, compared to the millions of times that distance in our local spiral arm. As we approach this stellar metropolis, we see a variety of star types. Young, massive stars shine brightly with blue-white light. These are relatively short-lived and reveal recent bursts of star formation activity. Mixed in with them are aged, reddish stars that have long since exhausted the hydrogen fuel in their cores, burning helium and heavier elements instead in more advanced stages of their lives. The crowding among these stars has significant consequences for their interactions. On the outskirts of the galaxy like Earth, stars can exist happily for billions of years without significant disturbance. But in the center, gravitational pulls from neighboring stars and dense gas clouds often lead to complex encounters. Stars can steal material from each other, merge, or be flung off in new directions, events that shape the evolution of the galactic center over time. Now moving closer, what really draws attention is the presence of an intense source of energy and gravity. This isn't just a bright star cluster or a supernova remnant. It's something far more powerful and mysterious. A supermassive black hole known as Sagittarius A, or SGR-A for short. This black hole contains the mass equivalent to about 4 million suns packed into a space no larger than our solar system. Despite the name, black holes themselves emit no light. Instead, what we observe is the effect they have on their surroundings. Stars in the immediate vicinity of SGR orbit at astonishing speeds, some completing their orbits in just a few decades or less, movements tracked by astronomers over the past 30 years to confirm the central black hole's existence. Gas clouds surrounding the black hole are heated to extreme temperatures as they fall inward, emitting X-rays and radio waves. Occasionally, bursts of energy erupt when the black hole interacts with clumps of matter, creating flares detected by space telescopes. This supermassive black hole acts as the gravitational anchor of the galaxy, holding billions of stars in orbit and influencing the shape and rotation of the Milky Way. Although it is incredibly massive, the total mass of the black hole is still only a tiny fraction of the mass in stars and gas in the region. However, its gravitational influence is profound, shaping star formation and the dynamics of material in its immediate neighborhood. Surrounding SGR-A is a thick, swirling disk of gas, and thus known as the circumnuclear disk. This structure extends for a few light years and is composed of molecular gas clumped into turbulent clouds. Within these clouds, the conditions are ripe for the birth of new stars, though the environment here is far from serene. Intense radiation, strong magnetic fields, and frequent shock waves from stellar winds and supernovae blasts make this a hostile setting for star formation compared to more peaceful parts of the galaxy. Despite the challenges, astronomers have detected young stars within a few light-years of the black hole, showing that nature continues to find a way to spark new generations of stars even amidst the chaos. These young stars, often clustered in tight groups known as star clusters, orbit the black hole in patterns that reveal the complex gravitational dance happening in this crowded place. We also observe a variety of energetic phenomena in the galactic center that mark it as far from an ordinary neighborhood. High-energy cosmic rays, powerful magnetic fields, and strong X-ray and gamma-ray emissions create an environment more extreme than anything experienced near Earth. Instruments onboard space observatories like the Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope have mapped these emissions, providing insights into processes like particle acceleration and magnetic reconnection. A significant source of energy in the galactic center is supernova explosions, massive stars ending their lives in spectacular blasts. These events release vast amounts of material and energy, triggering shock waves that compress nearby gas clouds and can spark new star formation or disrupt existing stars and gas distributions. The supernova remnants visible in radio and X-ray wavelengths map the tumultuous processes shaping the galactic core. Another astonishing feature revealed by radio and infrared telescopes is the presence of enormous filaments of magnetized plasma extending tens of light years above and below the galactic center. These filaments, aligned in complex patterns, suggest strong, organized magnetic fields sculpting the interstellar medium. Understanding their origin is an active area of research. They may result from interactions involving stellar winds, supernovae, or the central black hole itself. Although the galactic center is packed with high-density stars and energetic events, it is also a major reservoir of molecular gas, the raw material for star formation. This gas is mostly hydrogen, existing in cooler, denser molecular clouds shielded from intense radiation. The presence of abundant gas means that, despite harsh conditions, the cycle of star birth and death continues, contributing to the ongoing evolution of the region. One of the challenges astronomers face when studying the galactic center is that it's obscured at visible wavelengths by thick clouds of dust and gas. This dust blocks much of the light from stars and other sources, making direct observation difficult. To overcome this, scientists rely on infrared, radio, X-ray, and gamma-ray observations, which can penetrate these murky veils. Infrared telescopes, like those aboard the Hubble Space Telescope and ground-based observatories equipped with adaptive optics, allow us to see through the dust and capture images of individual stars orbiting SGR-A. The data collected over decades from various wavelengths have allowed astronomers to build detailed three-dimensional models of the region, estimate the mass distribution, map gas flows, and track stellar motions. These observations continue to refine our knowledge of how galaxies like the Milky Way function at their cores. Moving beyond the immediate black hole environment, the galactic center features a ring-like structure of star-forming activity known as the central molecular zone, stretching over several hundred light-years. This zone, rich in dense molecular gas, is one of the most active star-forming regions in our galaxy. The large amount of material available and the energetic processes ongoing there make it a fascinating laboratory for understanding the birth conditions of stars under extreme circumstances. Within this central molecular zone, clouds of gas have been studied in detail, revealing a mixture of dense cores where stars are formed and more diffuse regions influenced by turbulence and magnetic fields. Giant molecular clouds such as SGR-BETWO stand out as some of the largest and most massive structures in the Milky Way, places where complex organic molecules have been detected, indicating the potential for the chemical precursors of life to arise even in these turbulent zones. The discovery of complex organic molecules in the galactic center also opens questions about the chemistry and conditions that might have existed during the early stages of our solar system and broader galactic evolution. By studying such clouds, researchers can learn how molecules important for biology on Earth might form in space. Overall, the galactic center is a dynamic, evolving region marked by intense gravitational forces, incredible energy releases, and continuous cycles of matter transforming from gas clouds to stars and back again. Far from a static, empty void, this is a place where physical laws play out on scales and intensities that challenge our understanding, enriching astrophysics and cosmology in countless ways. As we continue to piece together observations, the center of the Milky Way remains an extraordinary natural laboratory, one that pushes our technology and theories to their limits. Every new discovery here adds a puzzle piece to understanding the life and evolution of galaxies, including the complex interactions between stars, gas, black holes, and the large-scale structure of the universe. Preparing to leave the immediate environment of Sagittarius A, we can reflect on how this compact region influences not just its own vicinity, but the entire Milky Way's structure. The gravitational pull of the black hole and the distribution of stars in the bulge, an accumulation of older stars surrounding the center, help maintain the galaxy's spiral shape and rotational properties. Furthermore, this central bulge is not a simple, uniform sphere, but shows intricate kinematics and chemical variety that tell stories about the Milky Way's formation history. Some of the stars here are among the oldest in the galaxy, carrying chemical fingerprints that provide a window into the early universe and the processes that built up galaxies over billions of years. By studying the galactic center with ever-improving instruments, scientists can test theories of galaxy formation and evolution. They try to understand how supermassive black holes grow and influence their host galaxies, a relationship that appears crucial across cosmic history. The Milky Way's center serves as a nearby example, allowing detailed scrutiny impossible for galaxies millions or billions of light-years away. This ongoing research is powered by military-grade precision instruments on Earth and in space, such as the Very Large Telescope in Chile, the Atacama Large Millimeter/Submillimeter Array, and the Event Horizon Telescope, famed for capturing the first image of a black hole in another galaxy. In the case of SGR-A, the Event Horizon Telescope project is actively working to produce the first direct image of our black hole's event horizon, the boundary beyond which nothing, not even light, can escape. Such an achievement would mark a major milestone in astrophysics, deepening our understanding of strong gravity and general relativity in action. As technology advances, future space missions and observatories will probe the galactic center with greater sensitivity and resolution. Instruments like the James Webb Space Telescope, launched recently, expand our view in the infrared, potentially uncovering new details about star formation, molecular clouds, and the environment immediately around the black hole. By standing at the edge of this cosmic furnace, the center of our galaxy, we glimpse the intricate interplay between gravity, matter, and energy governing the galaxy's evolution. What seemed for many years to be an inaccessible, chaotic, and forbidding region is now revealed as a place of profound scientific importance and wonder, accessible through human ingenuity and exploration. From this vantage point, we can appreciate how the center of the Milky Way is not just a subject of distant fascination, but a key to unlocking cosmic mysteries fundamental to our place in the universe. Through continued observation and theoretical modeling, the galactic center will remain one of the most exciting frontiers in astronomy for decades to come. Beyond the immediate surroundings of the supermassive black hole and the densely packed stellar bulge, the broader environment of the galactic center presents a fascinating interplay of extreme conditions that have captured the attention of astronomers for decades. One particularly important aspect is how the energy output from the black hole and the surrounding energetic events influence the material in this region and potentially impact the galaxy on much larger scales. While Sagittarius A is relatively quiet compared to the active supermassive black holes found at the centers of many other galaxies, it still produces occasional bursts of X-rays and radio waves. These emissions are clues to small amounts of matter spiraling in and being heated to millions of degrees. The black hole operates as a sort of cosmic thermostat, regulating how gas clouds cool and collapse, which in turn influences the rate of star formation nearby. Understanding this feedback loop between the black hole's activity and its environment can give insight into why galaxies like ours develop the way they do. Coupled with this are the effects of powerful stellar winds, streams of charged particles, blown off by massive stars in the center. These winds collide with surrounding gas and dust, creating shock waves and heating the interstellar medium. The cumulative effect of thousands of these combined winds forms a turbulent environment that stirs the gas clouds, driving turbulence on scales up to tens of light years. This turbulence plays a crucial role in controlling whether gas can settle down to form new stars, or whether it's too chaotic for efficient star birth. Another compelling feature shaping the galactic center is the cluster of massive star clusters located within just a few tens of light years from Sagittarius A. For instance, the quintuplet and Arches clusters are among the most massive and luminous star groups in the Milky Way. These clusters contain hundreds of young, hot stars that emit intense ultraviolet radiation. This radiation ionizes the surrounding gas, stripping electrons from atoms and turning it into plasma. The ionized gas then glows in infrared and radio wavelengths, producing beautiful and intricate nebulae, as mapped by infrared telescopes. These young clusters, only a few million years old, suggest that despite the hostile environment, star formation has not only occurred, but continues to occur at a relatively brisk pace. Their presence challenges earlier assumptions that the environment near a supermassive black hole might be too violent for stars to form. Instead, it appears that star formation in the galactic center operates under a unique mode, likely influenced by both the strong gravity and the energetic feedback from stars themselves, that differs from the calmer regions of the galaxy. Moving farther out into the galactic bulge, beyond a few hundred light years from the central black hole, the environment begins to shift. Here, the density of stars gradually decreases, and the composition becomes more dominated by older, red giant stars and remnants of past generations such as white dwarfs and neutron stars. This bulge forms an elliptical-like structure surrounding the center, comprising roughly 1 billion stars, and accounting for a significant portion of the Milky Way's total mass. The bulge's stars provide a rich fossil record of the galaxy's evolutionary past. By studying their motions and chemical compositions, astronomers can piece together the history of how the Milky Way assembled itself, including whether it grew through steady accretion or violent mergers with smaller galaxies. The galactic center acts as a gravitational anchor, but the bulge's structure and properties reflect a complex chronology of star formation and dynamical evolution happening over billions of years. An exciting development in this field has come from the field of stellar archaeology, where researchers analyze the abundance of elements heavier than helium, referred to as metallicity, in these bulge stars. It turns out that stars closer to the galactic center tend to have higher metallicities compared to stars farther out in the galaxy. This implies that the inner regions experienced intense and repeated cycles of star formation and supernova explosions early on, enriching the gas with heavier elements that later generations of stars incorporated. Understanding these chemical gradients helps us trace the timeline and efficiency of early star formation and how matter cycled through multiple generations. One intriguing structure within the bulge is the X-shaped distribution that appears when astronomers chart stars' positions and motions in 3 dimensions. The bulge isn't simply a smooth, spheroidal clump, but exhibits this boxy or peanut-shaped feature, likely the result of the dynamic influence of the galaxy's stellar bar. The bar is an elongated, dense region of stars that extends several thousand light years from the center, acting as a large-scale conveyor belt funneling gas inward. This inflow of gas helps feed star formation in the central molecular zone and potentially the black hole itself. The presence of this bar structure has implications for the Milky Way's dynamics. It can trigger spiral arms, redistribute angular momentum, and foster the conditions for bursts of star formation along its length. The interplay between the bar, the bulge, and the central black hole's gravity shapes the galaxy's morphology and ongoing evolution, linking structures on scales from thousands of light years down to a few light years. Another characteristic feature within the central few hundred light years is the abundance of molecular clouds. Unlike the more diffuse atomic hydrogen found in other parts of the galaxy, molecular clouds are made of hydrogen molecules, H2O, and other gases and dust that serve as the raw material for new stars. In the galactic center, these clouds are hotter and denser than those found in quieter regions of the Milky Way, a reflection of the intense environment. One of the standout molecular clouds is Sagittarius B, one of the galaxy's most massive and complex star-forming regions. Extending dozens of light years, SGR Beatwo is rich in a variety of molecules, some of which are quite complex organic compounds with many atoms, including carbon, hydrogen, oxygen, and nitrogen. The discovery of such molecules provides a chemical link to prebiotic chemistry, the kinds of processes that might ultimately lead to life, far beyond the boundaries of our solar system. The extreme conditions in the galactic center make the survival and formation of these complex molecules surprising and intriguing. Researchers are still trying to understand how molecules persist despite intense radiation and strong shock waves. Studying these clouds helps shed light on the chemical pathways at work in space and the potential for molecular complexity amid extreme environments. Adding to the complexity of the galactic center's physical environment are the strong magnetic fields threading through the interstellar gas. These fields influence the motion of charged particles, helping shape the morphology of molecular clouds, affect star formation rates, and even contribute to the confinement and acceleration of cosmic rays, high-energy particles traveling near the speed of light. Observations at radio wavelengths have revealed filamentary structures, long, narrow strands of magnetized plasma climbing hundreds of light years above and below the galactic plane. The origin of these filaments is still not fully understood, but they appear to be related to energetic events such as supernova explosions or outflows from the black hole region. Magnetic fields in these filaments could channel energetic particles and affect the distribution of gas throughout the galactic center and beyond. Supernova explosions are another critical factor in this environment. When massive stars exhaust their nuclear fuel, they often end their lives in titanic blasts that release enormous amounts of energy. These explosions enrich their surroundings with heavy elements formed in the star's cores and drive shock waves that compress nearby gas, triggering waves of new star formation, or conversely, dispersing clouds and suppressing star birth depending on local conditions. Remnants of past supernovae are seen in X-ray and radio observations as expanding shells and bubbles of hot gas. Some of these remnants appear clustered in regions close to the galactic center, indicating star formation activity in previous epochs. The balance between star birth and death in the core region is dynamic, with feedback from massive stars shaping the environment on multiple scales. Cosmic rays, high-energy particles often accelerated by supernova shocks or interactions near the black hole, further influence the galactic center. These particles penetrate molecular clouds, ionizing gases and affecting their chemistry. The presence of intense cosmic ray fluxes is one explanation for the warmer temperatures observed in molecular clouds in this region compared to similar clouds elsewhere in the galaxy. One consequence of all these energetic processes is the presence of large-scale outflows, streams of gas pushed away from the galactic center at high speeds. Recent discoveries, including the famous Fermi bubbles, giant lobes emitting gamma rays that extend tens of thousands of light-years above and below the galactic plane, indicate that the Milky Way has experienced episodes of powerful energetic events in the past, possibly linked to periods of increased activity from Sagittarius A or bursts of star formation. These outflows likely transport gas, magnetic fields, and cosmic rays into the galactic halo, influencing the Milky Way's evolution and the surrounding intergalactic environment. The exact origin and age of the Fermi bubbles remain subjects of ongoing research, but their discovery demonstrates just how dynamic the center of our galaxy is on vast scales. Underpinning all these phenomena is the incredible complexity of the galactic center's interstellar medium, the gas and dust filling the space between stars. This medium is far from uniform. Observations reveal a patchwork of dense molecular clouds, ionized plasma, turbulent gas flows, magnetic filaments, and diffuse atomic gas, all interacting under the influence of gravity, radiation, and magnetic forces. One fascinating aspect is how the interplay between these components shapes the rate of star formation and gas dynamics in this region. Despite enriched gas supplies and turbulence, the net star formation rate in the galactic center is lower than expected based solely on gas densities, a situation sometimes referred to as a star formation deficiency. Determining why this occurs helps astronomers understand how physical conditions either promote or inhibit the birth of stars. The study of the galactic center extends beyond just observational astronomy. Theoretical models and computer simulations play a critical role in explaining how these various ingredients interact. By combining multi-wavelength data with simulations of gas dynamics, star formation, and black hole feedback, scientists work to reconstruct the complex history of the region and predict future evolution. As new instruments come online with improved sensitivity and higher resolution, the precision with which we can study phenomena in the galactic center will increase dramatically. The James Webb Space Telescope, for instance, promises unprecedented views of the dusty, obscured regions in infrared light, potentially uncovering previously hidden stellar populations and providing sharper images of the molecular clouds and star clusters. Similarly, next-generation radio observatories like the Square Kilometre Array will sharpen our understanding of the magnetic fields and cosmic ray population in finer detail. Meanwhile, X-ray observatories will continue to trace phenomena linked to stellar deaths and the feeding of the central black hole. In essence, the center of the Milky Way serves as a natural laboratory where multiple branches of astrophysics converge: stellar evolution, high-energy astrophysics, galactic dynamics, magnetohydrodynamics, and astrochemistry, to inform us about the processes operating not only in our galaxy, but likely in many galaxies throughout the universe. Exploring this region helps place our solar neighborhood in context. While we live in a relatively quiet spot on the outskirts of the Milky Way, understanding the bustling environment of the galactic center clarifies the extremes of environments under which stars and planets might form and evolve. It also deepens our grasp of how galaxies grow and mature through continuous cycles of matter and energy. In sum, the center of the Milky Way combines the extremes of cosmic conditions: intense gravity, powerful magnetic fields, energetic particle acceleration, and continuous transformation of matter. This combination makes it an indispensable focus of modern astronomy and an ever-fascinating destination in our quest to understand the cosmos. As we expand our view beyond the core itself, an intriguing feature comes into focus: the Milky Way's central bar. This elongated, cigar-shaped structure, composed of stars, gas, and dust, extends several thousand light-years across the central region of the galaxy. The bar exerts a significant influence on how material moves within the inner Milky Way. Acting like a gravitational engine, it channels gas from the galaxy's spiral arms inward toward the center, fueling bursts of star formation and potentially contributing mass to the central black hole over time. Bars are common features in spiral galaxies, and studying ours offers valuable clues about how these structures affect galactic dynamics. The gravitational forces from the bar cause stars and gas clouds to follow elongated orbits rather than perfect circles, creating zones of compression where gas piles up and cools enough to collapse into new stars. This process happens along the length of the bar and often leads to the formation of dense molecular clouds within a few hundred light-years from the galactic center. One consequence of the bar's action is the Central Molecular Zone, CMZ, an area rich with dense molecular gas and active star formation. The CMZ stretches across roughly 600 light-years and contains some of the most massive and turbulent molecular clouds in the entire Milky Way. It's within this zone that many of the young massive star clusters, like the Arches and Quintuplet clusters, reside, illustrating the ongoing cycle of star birth even under extraordinary conditions. Considering the CMZ's complex environment helps us appreciate the delicate balance maintained between gas inflow and star formation. While the bar funnels large amounts of gas inward, the intense radiation, stellar winds, and supernova explosions from new stars inject energy back into the cloud environment, often dispersing or heating the gas to delay or even halt further star formation. This kind of feedback loop is essential in shaping the galactic center's evolution and is a key focus of astrophysical research today. Moving from the structural to the chemical, another remarkable aspect of the galactic center region is its rich chemical diversity. Observations of molecular clouds in this area reveal an abundance of complex molecules, some of which are fundamental building blocks for prebiotic chemistry. Molecules such as formaldehyde, methanol, and even more intricate carbon-based compounds have been detected within clouds like Sagittarius A. This particular cloud is not only notable for its size and density, but also for being one of the richest chemical reservoirs in our galaxy. The presence of such complex molecules amid the turbulent and energetic environment is fascinating because it challenges our understanding of chemical processes in space. These molecules form primarily on the surfaces of tiny dust grains, where atoms and simpler molecules stick, react, and eventually break free into the surrounding gas. Despite the harsh radiation and shock waves pervasive in the galactic center, these processes continue, indicating a remarkable resilience of astrochemical pathways. Exploring this chemistry isn't just an academic exercise. It gives us clues about the origins of life's ingredients across the universe. The molecular complexity in regions like Sagittarius A suggests that the basic components of life may arise naturally in diverse cosmic environments, far beyond the calm conditions typical of planet-forming disks. This realization broadens our perspective on the potential distribution of organic chemistry and possibly life elsewhere in the galaxy. Delving deeper into the interstellar medium, magnetic fields play a critical role in shaping the galactic center's behavior. These fields, though invisible, guide charged particles in the plasma, ionized gas, that populates much of the space between stars. They can control the flow of gas within molecular clouds, influence the formation of filamentary structures, and affect the acceleration and confinement of cosmic rays. Magnetic filaments near the galactic center are among the most striking manifestations of these forces. These long, slender strands, stretching for tens of light years and aligned vertically relative to the galactic plane, are highly magnetized and glow brightly in radio wavelengths. Their origin remains an open question, with hypotheses ranging from outflows driven by supernova explosions or stellar winds to interactions related to the central black hole's activity. The energy stored in these magnetic fields impacts the dynamics of gas and star formation. For instance, strong fields can support clouds against gravitational collapse, preventing premature or excessive star birth. They also affect shock propagation during supernova events, and may even participate in generating some of the high-energy emissions observed in this region, contributing to the galactic center's reputation as a cosmic powerhouse. Supernovae, the explosive deaths of massive stars, are another fundamental factor in shaping the galactic center's environment. With a higher concentration of massive stars, this region experiences frequent supernova events, injecting substantial amounts of energy, radiation, and heavy elements into the interstellar medium. The blast waves from these explosions sweep through nearby gas clouds, compressing and heating them. This can cause clouds to collapse under their own gravity, sparking new waves of star formation, or alternatively, disperse gas, hindering star birth depending on local conditions. Supernova remnants near the galactic center, observed in radio and X-ray bands, provide a dynamic snapshot of this ongoing cycle. The shock waves from these remnants drive turbulence, maintain high temperatures, and stir the complicated mixture of gas phases, from hot, ionized plasma to cooler, dense molecular clouds, making the galactic center a highly heterogeneous environment. Cosmic rays, charged particles accelerated to nearly the speed of light, add an additional layer to this energetic milieu. These particles originate primarily from supernova remnants and possibly from processes near the black hole itself. Once accelerated, cosmic rays permeate molecular clouds, partially ionizing the gas and influencing its chemistry and thermal balance. The abundant cosmic ray flux in the galactic center partly explains why molecular clouds here appear warmer than those in the galactic disk far from the core. Unlike regions where ultraviolet radiation dominates heating, in the galactic center cosmic ray ionization plays a significant role, maintaining molecular gas temperatures at elevated levels of around 50 to 100 Kelvin, compared to the lower temperatures typically found elsewhere in the galaxy. Looking even broader, observations reveal large-scale outflows and structures extending far beyond the central few hundred light-years. Among the most remarkable are the Fermi bubbles, vast lobes of high-energy gamma-ray emission rising up to 25,000 light-years above and below the Milky Way's plane. Discovered using the Fermi Gamma-Ray Space Telescope, these bubbles are evidence of energetic events in the galactic center's past, possibly linked either to past active phases of Sagittarius A or to intense star formation bursts driving collective winds. These bubbles show that the influence of the galactic center is not confined to its immediate vicinity, but reaches into the galaxy's halo, affecting gas circulation and magnetic field configurations on enormous scales. They also offer important insights into feedback mechanisms, where energy injected by the central black hole or stellar activity plays a crucial role in regulating the galaxy's evolution. In sum, the galactic center is a hub of complex, interconnected processes, from the gravitational influence of the central black hole and the dynamic motions induced by the bar, to the chemical richness of molecular clouds, the shaping power of magnetic fields, and the turbulent aftermath of supernovae. Together, these components form a system whose study not only reveals how our own galaxy functions, but also provides a template to understand active galactic centers throughout the universe. As observational technologies and theoretical models continue to improve, scientists are steadily uncovering new layers of detail about this region. The insights gained deepen our knowledge of fundamental astrophysical processes such as star formation, gas dynamics, and the roles played by black holes and magnetic fields. All of this underscores the galactic center as one of the most fascinating and informative places to study, an astrophysical laboratory literally in our cosmic backyard. Another essential element to consider when exploring the center of the Milky Way is how the dynamics of stars and gas are influenced by the galaxy's rotation and the presence of resonant structures created by the gravitational interplay within the bar and bulge. These resonances act like traffic patterns on a galactic scale, where stars and gas clouds are organized into specific orbits based on the gravitational forces they experience. One of the key resonances is known as the inner Lindblad resonance, ILR. At this radius within the galaxy, the gravitational influence of the bar causes gas clouds to settle into elongated orbits, effectively piling up and slowing down their radial motion toward the center. The ILR acts as a sort of bottleneck concentrating gas, and often triggering star formation rings or enhanced molecular cloud densities. In the Milky Way, the ILR helps define the boundaries of the central molecular zone, containing much of the dense molecular gas we have discussed. At these resonances, gas flowing inward hits regions where the gravitational forces tug in different directions, causing the gas to compress and heat, sometimes sparking bursts of star formation or shock waves that alter the local environment. Observing the dynamics around these resonances aids astronomers in understanding how the Milky Way redistributes material and regulates star formation near its core. Adding to the complexity are the intricate stellar orbits shaped by the central bar. Unlike the nearly circular paths stars take in the outer galactic disk, those in the bar region often follow elongated, oval-like orbits aligned with the bar's orientation. These orbits facilitate the transport of material inward, effectively funneling gas from the galaxy's spiral arms down into the circumnuclear environment. This movement feeds the central molecular zone and ultimately supplies material that keeps feeding star formation and potentially the growth of the supermassive black hole. The idea that the bar can drive gas inward towards the center connects to observations of similar structures in other galaxies, where bars often correlate with active central regions and nuclear starbursts, periods of intense star formation. For the Milky Way, the bar's role underscores the interconnectedness of galactic-scale structures, with processes occurring on scales many orders of magnitude smaller. Building on this understanding, another fascinating aspect is the recent evidence for episodic or bursty activity in the galactic center. Astronomical records show that the black hole and surrounding star clusters haven't always been in a steady state. Instead, there have likely been phases where the central black hole was much more active, accreting large amounts of material and producing powerful outflows and radiation bursts. One way to trace this history is by studying the so-called light echoes, reflections of past X-ray outbursts seen in the surrounding molecular clouds. These clouds act like cosmic mirrors, scattering high-energy radiation and providing timestamps of energetic events that occurred hundreds or thousands of years ago. Such measurements suggest that Sagittarius A was hundreds or even thousands of times brighter in the recent past compared to its current quiet state. These periods of heightened activity might tie into the formation of the Fermi bubbles, the enormous gamma-ray emitting lobes that stretch above and below the galactic plane. The bubbles are thought to be remnants of energetic events like strong jets or winds launched by the black hole or collective effects of starburst-driven winds, hinting that the galactic center cycles through phases of quiet and intense activity on timescales of millions of years. Understanding the factors that cause these transitions is a major goal of current astrophysical research and is closely linked to how matter flows into the black hole's grasp. Because the black hole's feeding is regulated by the availability of gas and the gravitational forces pushing it inward, any changes in the galactic environment, such as increased gas inflow from the bar or nearby star formation bursts, could trigger these outbursts. Shifting focus slightly, the role of star clusters near the galactic center offers more insights into the region's evolutionary narrative. The arches and quintuplet clusters, as mentioned earlier, are not just young populations of stars, but also extreme environments that challenge our theories of star formation. These clusters contain stars many times more massive than the Sun, shining with intense ultraviolet radiation that affects the surrounding medium. The winds from these massive stars generate powerful shocks and ionize gas far beyond the cluster boundaries, contributing to the overall energetic state near the galactic center. Importantly, studying these clusters helps astronomers understand how massive stars live and die in crowded, high-pressure environments that differ drastically from more tranquil regions like our solar neighborhood. One notable question concerns the origin of these clusters. How do such massive groups form so close to a supermassive black hole, where strong tidal forces could tear apart large gas clouds before they collapse? Current models suggest that these clusters might have formed farther out in the central molecular zone and then migrated inward over millions of years, or that the star formation process itself operates differently under intense gravitational and radiative pressures. Understanding these formation mechanisms is critical not only for galactic center studies, but also for explaining the formation of dense stellar systems elsewhere, such as globular clusters or starburst regions in other galaxies. While the gravitational environment near the galactic center is extreme, it also serves as a natural testing ground for stellar evolution under unique conditions. For example, massive stars in this region often lose mass much faster due to strong stellar winds, which affect their lifetimes and eventual end states as supernova explosions. Some of the most massive stars here end their lives as neutron stars or black holes, potentially adding to the population of compact objects orbiting close to Sagittarius A. This dense population of compact remnants influences the dynamics around the black hole as well. Some neutron stars and smaller black holes are thought to wander through the region, occasionally merging or interacting gravitationally, possibly producing detectable gravitational waves or X-ray emission. Detecting and understanding this compact object population provides another piece in the puzzle of how the galactic center evolves dynamically. Speaking of gravitational waves, the galactic center might be a site for interesting gravitational wave sources. Collisions or close encounters between compact objects, or small black holes spiraling into the supermassive black hole, are predicted events that observatories like LIGO, Virgo, and the upcoming LISA mission aim to detect. These gravitational waves offer an entirely different way to probe the dense and energetic environment near Sagittarius A, complementing electromagnetic observations. Meanwhile, advanced techniques like very long baseline interferometry, VLBI, continue to improve imaging and measurement precision around the black hole's event horizon. Projects like the Event Horizon Telescope, EHT, aim to produce horizon-scale images of Sagittarius A, akin to the famous first black hole image captured in the galaxy MADI 7. These efforts will allow astronomers to test predictions of Einstein's general relativity in the strong gravity regime, and could reveal details about black hole spin, accretion physics, and magnetic fields. Aside from the black hole itself, the galactic center also serves as a natural collider and nursery for exotic astrophysical phenomena. For example, pulsars, which are rapidly rotating neutron stars emitting beams of radiation, are predicted to exist in abundance here, but surprisingly few have been detected. This missing pulsar problem is an active area of research, with possibilities including radio wave absorption by dense gas or rapid pulsar spin-down due to magnetic field interactions. Discovering and studying pulsars in the central region would be highly valuable, as their predictable pulsing signals could act as precise clocks orbiting the supermassive black hole. This would provide an unprecedented laboratory to test gravitational theories and measure properties of the spacetime around Sagittarius A with exquisite accuracy. The galactic center's environment is also rich in phenomena related to magnetic reconnection, a process where magnetic field lines break and reconnect, releasing vast amounts of energy. This mechanism, well observed on the Sun, is likely at work here, contributing to the flares and energetic outbursts detected from the central black hole and surrounding plasma. Magnetic reconnection can accelerate particles to near-light speeds, adding to the cosmic ray flux and potentially powering some of the X-ray and gamma-ray emission. In fact, the complex magnetic field topology inferred from filamentary radio structures suggests a highly dynamic magnetized environment, one that not only influences star formation, but also modulates high-energy processes in the galactic center. Unraveling how these magnetic fields evolve and interact with gas and radiation is key to understanding the central region's structure. Moving back to the chemistry of the galactic center, the discovery of complex organic molecules points toward intriguing astrochemical pathways in an environment subjected to intense radiation and turbulence. Some molecules detected here are precursors to amino acids and other biologically relevant compounds, indicating that the basic raw materials for life might be ubiquitous throughout the galaxy, even in its most violent neighborhoods. Studying these molecules also provides clues about the physical conditions within molecular clouds, temperature, density, cosmic ray ionization rates, and how these factors influence molecular synthesis and destruction. Chemical models tailored to galactic center conditions help astronomers compare with observations and improve our understanding of molecular cloud evolution. Beyond organic chemistry, isotopic ratios in these clouds, ratios of slightly different atomic versions of elements, also offer insight into nucleosynthesis, the creation of elements inside stars or during supernovae. Measurements of these ratios help reconstruct the star formation history and the cycling of matter in the galaxy over cosmic time. Finally, as we consider the galactic center within the broader context of the Milky Way, it becomes clear that this region plays a central role in the galaxy's life cycle. The inflow of gas driven by the bar, the ongoing star formation in the central molecular zone, the dramatic interactions near the black hole, and the outflows reaching into the halo are all connected pieces of a complex feedback network. This network regulates how the Milky Way maintains itself, consuming gas to form stars, returning material and energy through stellar deaths and black hole activity, and reshaping its morphology via gravitational forces. Through continuous study, the galactic center not only reveals the mechanics behind our galaxy's heart, but also provides a blueprint for understanding similar processes in countless other galaxies throughout the universe. In coming years, the convergence of observational breakthroughs and advanced simulations promises to deepen our understanding of these processes. Instruments like JWST, the upcoming extremely large telescopes on the ground, and next-generation radio arrays will provide data of unprecedented detail, allowing us to probe everything from the inner workings of the accretion flow onto Sagittarius A to the complex chemistry and star formation cycles in the central molecular zone. As we unravel the galactic center's many secrets, we gain perspective on fundamental astrophysical questions. How do galaxies grow and evolve? How do supermassive black holes influence their host galaxies? And what conditions govern the birth of stars and the potential origins of life's building blocks on cosmic scales? The center of the Milky Way stands as a gateway to these answers, inviting ongoing exploration and discovery. To further appreciate the complexity of the Milky Way's center, it helps to consider the role of the galactic environment beyond stars, gas, and magnetic fields. That is, the presence and impact of dark matter in this region. Dark matter, though unseen and not directly detectable through electromagnetic radiation, constitutes the majority of the mass in galaxies, including our own. Its gravitational influence shapes how galaxies form and evolve over cosmic time. In the galactic center, dark matter contributes to the overall gravitational potential, combining with the ordinary or baryonic matter of stars, gas, and dust. The distribution of dark matter here is still the subject of active study, as it affects the orbits of stars and gas clouds, as well as the dynamics of the supermassive black hole's surroundings. Unlike the luminous components concentrated in the central few hundred light-years, dark matter is thought to form a more diffuse halo, enveloping the galaxy on much larger scales. However, simulations and indirect observational evidence suggest that the density of dark matter increases toward the center in a pattern known as a cuspy profile. This higher density near the galactic center influences the motions of stars and could even affect the growth and feeding rate of Sagittarius A by modulating the gravitational environment. Understanding the interplay between dark matter and visible matter in the core is crucial, as any unexpected deviations in stellar orbits could hint at dark matter's properties. For example, precise measurements of stars orbiting very close to SGR-A can test models of the dark matter distribution, shedding light on how this enigmatic substance behaves under extreme gravitational conditions. Speaking of the black hole, another intriguing aspect to explore is the possibility that Sagittarius A is not simply a passive gravitational well, but part of a dynamic system involving surrounding material and exotic physics. While its quiet demeanor contrasts with the violent active galactic nuclei seen in other galaxies, there are episodic activities, such as flares and accretion events, that astronomers watch closely. One area of investigation involves how gas accretes onto the black hole. Unlike the classic image of matter hurriedly falling inward, the actual process is complex and not fully understood. Recent theoretical models suggest that accretion flows around SGR-A may be radiatively inefficient, meaning much of the energy gets swallowed or carried away by winds rather than radiated as light. This contributes to the black hole's relatively low luminosity despite its enormous mass. Furthermore, Monitoring these flows in detail helps explain the nature of flares observed at X-ray and infrared wavelengths. These bursts are thought to arise from sudden magnetic reconnection events or instabilities in the hot plasma swirling near the event horizon, occasionally revealing otherwise hidden processes in strong gravity regimes. Beyond accretion physics, there's growing interest in how the black hole influences the dynamics of compact objects like stellar mass black holes, neutron stars, and white dwarfs clustered around it, known as the nuclear star cluster. The dense stellar environment near SGR-A encourages frequent gravitational interactions, leading to phenomena such as close stellar encounters, tidal disruptions, and the formation of exotic binary systems. For instance, when a star ventures too close to the black hole, tidal forces can tear it apart in a dramatic tidal disruption event, releasing vast energy and triggering bright flares. Although such events are rare in the Milky Way, they provide valuable insights into the behavior of matter under extreme gravitational stress. Additionally, the dense environment near the black hole may foster the formation of so-called extreme mass ratio inspirals, EMRIs, where stellar remnants gradually spiral inwards, emitting gravitational waves over long periods before final merging. These events are prime targets for future space-based gravitational wave detectors such as LISA, promising a new window into the heart of galaxies. Zooming out from individual stars and black holes to the large-scale evolution of the Milky Way, we see that the galactic center plays a prominent role in regulating the balance between star formation and feedback processes in the galaxy. Feedback in this context refers to the ways energy and matter returning to the interstellar environment influence subsequent generations of stars. For example, the combined effects of stellar winds, supernova blasts, and black hole activity inject energy and momentum into the surrounding gas. This feedback can prevent runaway star formation by heating and dispersing molecular clouds, but it can also trigger localized star formation by compressing gas clumps under the right conditions. The net result is a self-regulating ecosystem where the galactic center acts as both a nursery and a disruptor. Observations indicate that the current star formation rate in the CMZ is lower than what the dense molecular gas alone would suggest, a puzzle known as the star formation inefficiency phenomenon. Various hypotheses aim to explain this, including the role of strong magnetic fields that provide support against collapse, the impact of turbulence stirred by feedback, or the elevated temperature maintained by cosmic rays and shocks. Determining the dominant factors requires combining detailed observations with sophisticated computer simulations that model gas dynamics, magnetic fields, radiation, and gravity simultaneously. These simulations help test whether the observed inefficiency arises from the extreme environment of the galactic center or reflects a more general aspect of star formation physics. Another facet to consider is the chemical evolution of the galactic center compared to other parts of the Milky Way. Studies of stellar populations and gas chemistry reveal that the inner galaxy has experienced more rapid and efficient chemical enrichment. This translates to higher abundances of elements such as iron, oxygen, and carbon, reflecting the cumulative effects of many generations of massive stars producing heavy elements in their cores and dispersing them into the interstellar medium. Chemical signatures preserved in ancient stars help astrophysicists reconstruct the timeline of star formation and supernova activity. In particular, certain isotopic ratios and abundance patterns serve as chronometers, indicating that the galactic center underwent a bursty star formation history earlier than the galactic outskirts. These results provide constraints for galactic formation models, explaining how massive galaxies assemble their cores. Moving beyond the Milky Way itself, the study of our galactic center offers a baseline for understanding the behavior of active galactic nuclei, AGN, in other galaxies. While SGR-A is relatively quiet, many galaxies harbor supermassive black holes that unleash immense power, visible across the electromagnetic spectrum, sometimes outshining their entire hosts. Comparative studies show that the conditions and processes observed here scale up in active galaxies to produce phenomena such as bright quasar phases, powerful jets, and large-scale outflows that shape galaxy evolution on cosmological timescales. Understanding these scaled relationships helps uncover how common various galactic evolutionary pathways might be, and what factors determine the fate of galaxies in the universe. Finally, the galactic center continues to be a focus for technological innovation. New observatories coming online in the near future, such as the Extremely Large Telescope, ELT, the 30-meter telescope, TMT, and the Square Kilometer Array, SKA, promise to push the resolution and sensitivity boundaries. These instruments will allow astronomers to trace faint stellar populations, study gas motions in unprecedented detail, and map magnetic fields across wider areas with finer precision. Complementing these ground-based facilities will be space-based missions like the James Webb Space Telescope, performing infrared surveys that pierce through dust and reveal hidden star clusters and molecular structures. The synergy between such instruments will create a more complete understanding of how the predicted physical processes actually unfold. In sum, the galactic center is not just an intriguing zone in the Milky Way. It is a cornerstone for many branches of astrophysics. From the physics of black holes and extreme gravity to the chemistry of molecular clouds and the large-scale choreography of galactic structure, this region encapsulates essential aspects of how galaxies live, evolve, and connect to the broader cosmos. As our observational reach extends and theoretical frameworks mature, the Milky Way's center will remain an unparalleled laboratory, enabling breakthroughs that enrich our understanding of the universe, including the origin and fate of galaxies, and ultimately, our own cosmic origins.